Good afternoon, all of you. Now we are going to start our session. Will be taken by Professor Arijit Guha. Professor Arijit Guha received the PhD degree in electrical engineering in the branch of control systems from the Indian Institute of Technology, Kharagpur in 2018. He is currently working as an assistant professor in the Department of Electrical Engineering at National Institute of Technology, Rourkela, Odisha. Prior to that, he was worked as a senior R&D engineer at ABB Global Industries and Services Private Limited, Bengaluru, in the Industrial Automation Digital Division, and as a consultant at Samsung Research Institute, Bengaluru, in the in the Mobile Battery Research Division from August 2018 to May 2020. His current research interests include system identification, parameter and state estimation, fault diagnosis, um, prognostics, battery management system, electric vehicle, etc. Good afternoon, sir. So it's quite, we are happy to accept that you have accepted our invitations. So, sir, now you can start your session, sir.
Thank you, Professor Ghosh, for your nice introduction. And thank you for inviting me as one of the speakers on this occasion. So first, I would like to share the slide. Is my screen visible?
Yes, sir, your slide is visible to us.
Okay. So, so this is actually the topic that I'm going to present today. So the title is Online Health Monitoring of Rechargeable Batteries based on Artificial Neural Network. So as you can see that the application that where neural network has been applied, it is on battery, and it is on rechargeable batteries which can be actually charged and discharged repeatedly, like not like our some kind of battery which is once it is already one time it can be charged and then we have to throw it after it is fully drained. Okay, so and the main aspect is how to actually monitor the health of the battery online. Okay, so before we start, so I would just like to give you a brief introduction about that wherever ranging from portable electronic industries or towards the high-end applications like automotive industries, which includes the electric vehicles, hybrid electric vehicles, or plug-in hybrid electric vehicles. So all of them, all these kind of applications, they actually need a power source. Okay, so and batteries actually nowadays actually are very much useful in, and that's why the demand of batteries are increasing so much in last few decades. So we can see that we have like almost everyone actually uses a smartphone, so there also we have a battery. So battery, like whatever actually is there, so apart from that, certain attributes are there which are linked to the battery, which needs to be monitored periodically, just like SOC, which is a very common attribute, that is called the state of charge, and almost every device, it shows the battery state of charge, whether it is in a portable electronic device or in an automotive application like a electric car. Apart from that, state of health is also an important attribute which is of prime importance, and it tells you about the current health of the battery uh, relative to the battery, which like when actually the smartphone or the electric vehicle has been purchased. Okay, the current situation of the health. It says about the current health status of the battery. And the lithium ion battery chemistry, it has certain advantages. Okay, so apart from other kind of chemistries which are already available, so lithium ion has certain advantages. These are actually, this has been shown here. You can see that it has a longer cycle life, high energy density, high power density, low self discharge rate, and it is having a very smaller size. Okay, longer cycle life means it can be used for a longer time span by repeatedly charging and discharging, compared to other kinds of battery chemistries like nickel cadmium, nickel metal hydride, okay, or lead acid batteries, whichever is available in the market. And also it has a very high energy density, and that's why it is very much useful in electric cars, and it is having very compact size, and that's why you can actually mount it in an electric car, and it takes very less amount of space compared to other kinds of batteries if you think of. Okay, so other kind of chemistries, if you think, it will actually occupy a larger space compared to a lithium ion battery chemistry. And another advantage is the lower self discharge rate. Like if you charge a battery, lithium ion battery, and if you keep it idle for a long time, and if you observe that how much charge has drained, so you will observe that compared to other kinds of battery chemistries, as I said, nickel cad or nickel metal hydride, or lead acid batteries. So in case of lithium ion batteries, people have observed that the self discharge rate, like if we don't connect any load to the battery, which is acting like the source, if we don't connect any load, so it will, like due to some side reaction mechanisms inside the battery itself, there will be a self discharge. Okay, and that, due to that self discharge mechanism, so there will be like small amount of charge which is stored in the battery, it will be automatically, it will be discharged. Okay, just like suppose we charge the battery to 100%. Now if we observe the battery state of charge, say after 2 hours, even if we are not, suppose we consider a smartphone, now even if we don't play any song or run any app, there can be a reduction of the battery capacity from like state of charge, maybe by 1 or 2%. Okay, so that actually happens due to some self discharge mechanism. Okay, but compared to the other battery chemistries which are available in the market, the lithium ion battery chemistries, they have relatively much lower self discharge rate. Okay, so that is one of the major advantage. Okay, so due to these reasons, lithium-ion batteries are very much popular in this automotive sector and also the portable electronics industries. Okay, so now these are some of the different type of lithium-ion battery cells which are available in the market. So first of a kind, it is the coin cell, which it can be inside a smartwatch or any small device. And there are cylindrical cells which actually looks like this. So cylindrical cells actually can be connected in multiple numbers in series or in parallel combinations to make even bigger size battery modules or battery packs. Okay, basically in electric cars, not a single battery is used. It is basically a combination of many such batteries connected in series and parallel in order to actually maintain that much capacity which is required, and also the voltage levels. So this kind of cylindrical cells are very much used like while actually manufacturing battery packs. Apart from that, pouch cells are also very popular. Pouch cells actually looks like this. So in a smartphone, actually we have this kind of a cell. Okay, and this kind of cells, like a very popular model like A123 is available. So we can also connect series parallel combination of these pouch cells, and we can also form battery modules or battery packs. And apart from that, prismatic cells are also available. So these cylindrical cells, actually many manufacturers are there, like leading from Samsung, LG, Panasonic. Okay, so they all of them actually manufacture this kind of cells. which are commercially available. Okay, now coming to the basic battery operation, okay, and the related failure modes which are possible in during the operation of a battery. Okay, that actually I will first state. Then we will go to the actual problem. Okay, so here you can see that there are two figures. So this is basically the schematic diagram of a lithium-ion battery cell. Okay, so you can see that the first figure, it denotes the schematic diagram while the battery is getting charged. Okay, so here actually it is in the charging phase. So you can see that normally battery will have two electrodes, one is cathode and another is the anode. So this positive electrode that you can see here, it is basically the cathode and this is the anode. Okay, and they are basically uh, so they are basically connected by some current collectors. Okay, you can see this is a copper current collector which is connected to anode. This anode surface is mostly made of some graphite compound. Okay, carbon, which is actually you can see from this one redox reaction equation I have written here. You can see, and this cathode material, it can be some different compounds of lithium. Okay, like here I have written as lithium cobalt oxide. So apart from this, other kinds of cathode material is also possible, just like lithium iron phosphate, it is very popular. Okay, and lithium manganese dioxide, it is also very popular. And apart from this, there are also other kinds of lithium different variants are also possible. Okay, so now here what happens that these two electrodes, they are basically separated by a layer that you can see here in between. So this layer is called the separator. Okay, this separator is such kind of a layer. And another important thing is that there is electrolyte, okay, which is in the liquid form. So it is there, and inside the battery cell. And here what is happening that this is basically a porous layer. Okay, so and this kind of a layer is given for the protection of the battery. Okay, how the protection happens, like when battery is getting charged, so you can see that here this is the direction of current, you can see, and in the opposite direction there is electron flow. So now when actually you charge the battery, so lithium plus ions, they actually move from the cathode to the anode, okay, through the separator. This is basically a such kind of a porous layer that lithium ions can basically penetrate through, and from cathode to anode. So these lithium ions will pass, and therefore, like, because the current is in this direction, okay, and so electrons, we can realize that it is in the opposite direction. So there is basically, like, we are assuming that the direction of flow of electrons is this side, but there is no electron flow inside. Okay, so even if, like, the picture shows like this, but the direction of electron flow, but it is not happening through the separator. Okay, if it passes, there will be a short circuit. Okay, so current is flowing in the external circuit, which is here. Okay, outside. But inside actually the charge transfer, it happens due to the passage of lithium ions that we can see here. Okay, so this like arrow has been shown here just to show that the direction of electron movement is opposite to the direction of lithium ion movement. Okay, so now what happens that usually this separator is basically like a polyethylene polypropylene kind of a material it is used, and the electrolyte is basically like a lithium salt. Okay, it is made of some lithium salt. So here I have just denoted here that lithium hexafluorophosphate. So this is a kind of lithium salt, and basically what happens, the opposite thing happens when actually you discharge the battery. Discharging means you are connecting a load across the terminals. So these are basically the terminals. Okay, this is when the terminals are connected to the electrodes, they are not directly connected to the electrode. They are connected through these collectors. Okay, current collectors. That's why it has been shown here in the figure. And therefore, opposite thing is happening like when actually the discharging mechanism happens. So that time lithium ions they move in the opposite direction, and also similar to the similarly the electron flow is also in the opposite direction compared to what happened during the charging phase. Okay, and so therefore you can see now when actually the lithium ions pass from the cathode to the anode, from one electrode to the another electrode, so while actually it is passing, so it will experience some resistance in the path. Okay, that resistance that it faces, it is basically the internal resistance of the battery. Now every battery, whichever way it is manufactured, so there will be some internal resistance, okay, associated with all kinds of batteries. Now here what happens that due to repeated, like suppose you repeat this charging discharging for say 100 times. Okay, now what happens that due to repeated charging and discharging, so what happens, there will be some breakdown of the active material or the some lithium compounds, and that will be deposited on the surface of the anode. Okay, so this is actually one of the degradation mechanism which happens inside a lithium ion battery. Okay, so so this ACI that I have written here, it is called a solid electrolyte interface layer. Now electrodes, their number of electrodes are 2, and electrolyte is all over there. Okay, and therefore electrolyte and the two electrodes, they basically form a interfacing layer. Okay, just like normal capacitors, we understand there are two plates. Okay, and inside, like in between that, there is a dielectric. Okay, so therefore in this case two different kinds of layers actually form. Okay, so one between the electrode, the positive electrode and the electrolyte, another between the electrolyte and the anode or the negative electrode. So therefore charge is basically stored at those interfacing layers. Okay, that is actually the principal phenomena. So now while actually the battery is getting charged or discharged repeatedly, so this ACI layer, it forms on the anode surface, and because of that, whatever may be the internal resistance of the battery at the beginning, so eventually what happens, the due to the accumulation of ACI layer, which is basically some deposition of lithium compounds or active materials. Okay, so because of that, the overall internal resistance of the battery gradually it will increase. Okay, and as it increases, the number of lithiums that will take part in the charge storing mechanism, like it is called intercalation mechanism. So when lithium ions actually move from cathode to anode, so they actually take part in this intercalation, and therefore the charge that is stored on the interface layer of electrolyte and electrode, so due to repeated aging mechanism, the amount of charge that is stored, that actually becomes much less compared to when the battery is in new condition. Okay, and therefore the user actually they experiences a fall in the battery capacity after the battery has aged for a long time. Okay, so suppose you purchase a smartphone today, and you so now you charge the mobile phone battery and you actually use it for say 10 hours. Now once actually the battery, like the smartphone has become say 2 years old, so that time the same battery, it will not give you the backup of 10 hours. Okay, so eventually the battery capacity has reduced, and that happens due to the degradation mechanisms which are happening here. Okay, that as I said, these are the primary reasons. So because of that, the charge storing capability of the battery has reduced over time, and therefore maybe the battery will last for say 5 hours or so. Okay, so that happens due to repeated charging and discharging of the batteries, and also it depends on at what rate the battery has been charged. Like there are different kinds of chargers available, like so it depends, the degradation of the battery also depends on the rate of charging, rate of discharging. That is actually also a very important factor. And also we have to see that whether battery should not get overcharged or over discharged. Okay, so therefore there are certain internal factors, external factors which are responsible for battery degradation, and the so-called the failure mechanisms are accelerated. So here I have just listed some of them. So there can be internal short circuit due to a dendrite growth. Dendrite growth is something which is, if on this ACI layer, if there is a formation of metallic lithium crystal kind of structure, that will happen like here, and eventually it will try to puncture this separator, and it will connect the anode with the cathode, and in the meantime there will be a short circuit. Okay, and due to that short circuit, there can be like it can catch fire. Okay, just like some fire incidents it happened in Samsung Note 7 battery or in Ola electric bike. Okay, so so this is one of such internal factors which can actually eventually boil down to thermal runaway kind of catastrophe event. Okay, so now another thing that I have shown here, it is the chemical breakdown of electrode materials due to side reactions. Okay, side reactions is something which happens inside a battery, and due to that there can be a chemical breakdown of the electrode material, the material with which the electrode has been made. Like here it is a lithium cobalt oxide. So if there is a breakdown, there can be some internal fault inside a battery. Okay, and it also depends on temperature. Temperature is a very important factor. Like with increased temperature, what happens, this separator, so it has certain limit, like it will actually, like at higher temperatures it will there is a tendency that it may melt. Okay, so due to that melting there can be some shrinkage. Okay, so that may happen, that can be also a internal factor of battery failure. Also, as I said, that due to the deposition of ACI, so there is a overall increase in the internal resistance, and because the battery, it is a energy storing device or charge storing device. So you can actually think of like it is having some capacitive property. Okay, so capacitance you might have heard. So these are the basic elements in electrical engineering. So because there is a capacitive effect also along with the internal resistance, so overall there will be a change in the internal impedance. It is called the impedance parameter. When we actually take into account both resistance or capacitance, or if there are some other kind of device which also poses like some inductive property, so if we combine, so that will become a impedance. Okay, but in this case it is capacitive. Battery is basically having a capacitive nature. Okay, so that is actually one reason. Also there can be electrolyte breakdown, which is basically the breakdown of the electrolyte which is there inside the battery cell. Okay, there can be external factors, maybe due to overcharging or abnormal charging. Okay, that can happen. Like if we keep the maybe the mobile phone for overnight, so that will actually tend to overcharge the battery. Like even if it has reached 100%, so forcefully you are keeping it even for extended time or extended hours, so that actually eventually may happen, like may eventually degrade the battery, and it actually can like like after some time the usability of that battery actually may degrade and you may have to replace it. So here over discharge is also another mechanism by which battery can fail. Vibration or shock. Okay, so that is also one more reason. Like if you like suppose there is an electric car and there is a battery pack inside the electric car. Now suppose the electric car crashes with something, some hard object, so that will eventually like there will be some vibration or shock. Due to that also there can be faults which can be generated inside a battery. Okay, so therefore it can also act as an external factor. And increased temperature, decrease in the ambient temperature, that those are also reasons. Like people actually may use EVs in cold climates, also in some tropical weather. Okay, so ranging from different temperature zones in the world. So there can be like there is a change in the behavior because battery is an electrochemical device. You know that it is highly dependent on the ambient temperature. So the performance, it is actually the best performance we can get in a certain temperature range. But if it crosses like some lower limit or upper limit, that time we may face some, like there can be some malfunction. Okay. Now this is actually a graph that that I have put here. So this tells about like while actually you charge a battery. So this is a typical current profile and a voltage profile. So all these two quantities, they have been actually shown in the same graph in two different axes that you can see. So this is the time axis in the x direction, and there are basically two y axis. This y axis, it denotes the current and it is in amperes, and this is actually another y-axis which denotes the terminal voltage of a battery. Okay, so we will come across these terms soon. So when actually you charge a battery, so this is so in this case I have just shown two different kinds of uh, current profiles. So first one, actually it is like this part is basically called a probe cycle. So probe cycle is something where if we want to find some internal characteristics or parameters of a battery, so that time actually probe cycles are essential. Okay, otherwise actually probe cycles are not necessary. So because I will be showing you some example where probe cycle has been used, that's why. So probe cycle current is basically a very small magnitude of current, like much less than the rated current of the battery. Okay, so maybe suppose a battery you are using maybe of 3000 mAh battery. So maybe it is say one fifth of the 3000 milliamperes. Okay, so that kind of is like relatively much small compared to the normal charging current of a battery. Okay, normally the battery is charged at, like if you see the battery data sheets also, so they are normally charged at maybe 3000 mAh battery you can charge at 3 amperes. Okay, that is called a 1 C rate. Okay, or you can charge at 0.8 C rate. Okay, so C rate is something which is something like, suppose we have a battery of X ampere hours capacity. So if we charge the battery with X amperes, so that is actually called as 1 C rate. Okay, so that means you can actually now figure out that how much 0.8 C might be if the battery rated current is say 3000 mAh. Okay. Now this is here, like here what happens initially, like I can actually show you, because this is actually a bigger portion of it is like a probe cycle. So from here only I can explain you the fundamental charging procedure which is followed when actually, like even if you plug a phone for charging, or a battery pack inside an electric car. So this kind of this is actually a standard charging procedure where the battery the current which is applied to the battery, it is maintained constant, okay, for some time. Okay, so until when it is maintained constant, that every battery has a maximum like voltage limit, and there is a current limit. Okay, so the voltage limit or the upper limit, suppose in this case, so it is 4.4 something. Okay, 4.44 or something like that. So if you think that that is the maximum voltage, so constant current has to be actually supplied till that point, till the battery voltage reaches this 4.4 volt. Okay, so you can see here that initially the battery voltage was around say 3.5 or something, or slightly above 3.5. Okay, now once actually this current has been applied, so it has been maintained constant. Okay, so the battery charger is designed in such a way that it will provide the constant current for this much time interval, so that the battery voltage will reach the 4.4 volts, that is the maximum limit. Okay, now beyond that actually battery cannot be charged, it will not reach 4.8 or 5 volts. Okay, so there is actually the charger has been designed in such a way that once it touches the maximum limit of 4.4, so what happens, the voltage will be maintained constant. Now why it is done, because once the battery is reached, like it reaches 4 like maximum voltage, so up to that time the battery capacity, which is the battery state of charge, what you can see in a mobile phone, almost it reaches around more than 80%. Okay, so at this point the battery capacity, it has reached almost 80%. Now, rest of the 20%, you can actually do this constant voltage mode charging. So this is called a constant current mode charging, where current is maintained constant while the voltage is changing, you can see. And at this point, the voltage is maintained constant. Voltage is no longer changing, but the current is actually flowing down. Like it is, the magnitude is gradually decreasing. Okay, so that has certain reasons. Okay, so the current actually decreases, and this part is basically very slow process. Okay, so here in the picture you can't see much because I have not shown here the entire span, but here this constant voltage mode phase, actually it is a longer phase compared to constant current phase. Okay, now here 20% of the battery will get charged, and current, so when it will stop charging, because this current value, it will reach around say 6% of the battery rated current. That is basically the threshold. When it reached, so then actually the battery will stop charging. Okay, so till that time the battery voltage will be maintained constant at the upper limit. Now this part is called a discharging phase, where, so you can see that here the current was positive. Okay, compared to, like, you compare with this scale. So here the current is positive, you can see above zero. Now below zero, so current cannot be negative, right? So current is something like, we have denoted here negative just to denote it is discharging. Okay, that's it. So discharging actually mechanism, so it is drawing current, that's why the negative sign has been put here. Okay, now here you can see the current is in the negative direction because in the discharging phase, and this is basically a constant current discharge, because here also the current has been maintained constant throughout. Okay, and throughout this time span, the battery voltage, it actually gradually it is coming down, and here it reaches up to certain level, which is called the cutoff voltage. Okay, now this part is basically designed for a probe cycle. Okay, but similar kind of picture you will find here also. This is just like a bigger version, so that's why I explained from here, but actually the explanation is for this, it is for this part. Okay, so that's why it is here in the arrow mark, it is written normal CC charging used for state of health estimation. Okay, this part, this is the charging phase, like voltage is rising, and this is basically, this part is the probe cycle discharge, because this current corresponds to the probe cycle, but this current is normal charging current. Okay, so both actually I have shown here just to make you feel that probe cycle current is much smaller magnitude compared to the normal charging current. Okay, and why the probe cycle current is required, that actually I'll show you with one example there. So here you can see that this part is basically denotes the normal charging discharging phase, and this is the probe cycle. Okay, so now coming to this two key battery attributes. So one of this is the state of charge, what actually you you may be familiar. So it is basically the amount of capacity which is remaining with respect to the max capacity or the total capacity. Okay, so it is basically a ratio like this. So here that's why it is written total capacity minus capacity removed by total capacity into 100%. Okay, so basically the in your smartphone or any gadget, so you can see that this much amount of charge is left. So that, so in the green signal, like here you can see this is 100% charge. Okay, that's why the state of charge corresponding to this battery, it is 100%, while in this case you can see this is half. Okay, so here the battery state of charge, it is 50%. Okay, so this kind of symbols you can see in smartphones also, and here it is even less than 50%. Here this is completely drained. Okay, so ideally this is SOC 0%, but SOC 0% actually we should not actually like it is not encouraged to make SOC 0%. So therefore, like, battery should not be fully drained. Okay, so and also you actually should not like fully drain the battery. So before it reaches that level, you can actually charge it. Okay, maybe if it is 5-10% left, you can charge it. Okay, so that actually is very much essential. Like if you think that if you are going in a like traveling in a electric car, and suppose the battery, like whatever state of charge it is showing, it has reached up to this level, then all of a sudden in the middle of the way you can be stuck somewhere. So where if there is no charging facility anywhere, so therefore you need to be very careful. Okay, so you can actually charge it beforehand before it reaches up to this level. Okay, and battery state of health actually can be defined in terms of various parameters of a battery. One actually is the this first one is basically a very popular one, which is in terms of the battery capacity. Just like as I said, like battery capacity at this moment to the battery capacity at, so this BOL, it denotes the beginning of life, like when the battery is in a new condition. Okay, just like when, as I said, when you purchase a phone and if you charge it, so that time you may be getting a backup of 10 hours, but after you have aged the battery, like the smartphone, for 1.5 year or maybe 2 years, so there is a fall in the battery capacity. So that happens due to the reduction of the battery state of health. Okay, so that can be also defined in terms of internal resistance or power fading. Okay, now some of the uh, based on some literatures which are like prior literatures, so we have actually found some of the uh, shortcomings. So here, because this whatever I will be presenting here, it is like based on some partial charging data. Okay, so not fully charging data. Okay, so here some of the algorithms you can find that they can only estimate the battery state of health for same range of values for which the training has been performed. Okay, so suppose some algorithm you have designed in order to estimate the battery state of health. Okay, so battery state of health can be actually, you can get the information by using some algorithm. Okay, which is maybe a model based algorithm, like model based approach, or a data driven approach. Okay, now if some algorithm has been trained in such a way that for same range of values it has been trained, and actually it can perform the like SOH estimation in the same range, so that kind of algorithms are plenty. Okay, you can see in the literature. Also, like complete like complete charging and discharging battery data may be needed in order to train those algorithms which has been designed to estimate the battery state of health. Although actually the battery state of health you will not get like very frequently in actually the normally used smartphones, gadgets, or so these are actually still in the R&D phase. So in sometimes like in Apple smartphones, iPhones, actually sometimes you will get. So but in majority of the applications it is not there. Like majority of the applications, it doesn't actually give much information on the state of health. Okay, so state of health is a very important parameter based on which the user actually can take a decision whether the battery has to be replaced, or it has to be like it needs some maintenance very soon. Okay, so that decision is very much like it depends on the current state of health of the battery. Okay, now under practical usage, like if you see that a battery, like a battery which is undergoing charging discharging, so it is basically partial in nature. Okay, not like you may not actually always fully charge the battery or fully discharge the battery. Maybe it may happen that you fully charge the battery to 100%, but you have used 40% of it. Now when it reached 60%, again you have plugged it for charging. Okay, so that is basically partial discharge, not a full discharge. Okay, full discharge will only happen if you drain it from 100 to 0%. Okay, so most like it, therefore you can see that. And also, like when you charge a battery, when you charge a battery or discharge a battery, so suppose in a smartphone you are opening some app. Okay, or you are actually doing some, playing some games or listening some song, opening some video, so the, or you switch on the flashlight camera. So what happens that the 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 actually style of like usage, the usage pattern of the battery, like the way the power is consumed from the battery, it is not, it is actually very random in nature. It doesn't follow any pattern. Okay, so similar kind of characteristics you will also see in case of EVs. Okay, so when the EVs they are basically running on the road surface, so always actually the road surface will not be smooth. Sometimes there will be bumps ahead, sometimes there will be some steep slope, there can be some potholes. Okay, so some bumpers will come. Okay, or maybe due to traffic condition, actually you have to apply brakes and you have to accelerate depending on the situation. So therefore the pattern of charging and discharging, it is not a very deterministic kind of a thing. Okay, so it is very much random. So therefore, so these are actually the practical scenario, okay, that I'm talking about. And sometimes, like when you design some algorithms, so you need some special kind of probe signals. Okay, so which needs to be injected in order to find out the battery state of health information. Okay, but it is not always possible that if the battery is under usage, like already the battery is mounted inside a car or a smartphone, that time actually you cannot apply any probe signal and you can test it. Okay, whether probing signal is something which is like you want to study some internal characteristics of the battery in terms of the battery voltage and current information, and at the time you are giving a special kind of a like probe current signal, like maybe a very small magnitude or maybe a very high spike kind of a thing or a different kind of a pattern. Okay, just to for analysis purpose, that may not be always possible if you like if the battery is under usage. And also, like when the battery is not fully charging or discharging, so always you may have, like you may not have the cycle number information in like properly. So therefore there are some like you can find some reported methods so where battery models are used. Okay, but like if it is a model totally model based approach. Okay, so there can be some challenges, right? The battery model itself is a very sophisticated model. Like if you actually think of modeling the battery very accurately, so you actually have to model a battery electrochemical model. Okay, so electrochemistry is involved everywhere inside a battery. So those many parameters which are involved in an electrochemical model, along with the different kinds of reactions in different kinds of phases. So you actually have to have such knowledge. Like without knowing all such parameters, you cannot accurately estimate the battery state of health. Okay, so there are a lot of challenges in that. So that's why majority of the methods that we found in the literature, they are actually, they may be suitable for offline computation of the battery state of health, but online computation of the battery state of health is still actually a very challenging task. Okay, so therefore, like one method, like initial some work actually we have done. So that's why from there I'm just presenting some of the techniques that we have used. So some part of the work is still ongoing. So now here, based on the existing methods, so this is basically a comparison table. So we can see that for existing methods, so we need large amount of training data. And in our proposed method, so I will discuss that what method actually we are using. So in our proposed method, so here only we need some initial 400 cycles of data, and this 400 cycles of data means like by repeated charging discharging. Okay, and that approximately takes around 45 days, 1.5 months. Okay, time to generate that data. Okay, so without some initial data we cannot train our model, so we need such kind of prior data. Okay, just to train our models. After that we will apply those models and we will do our job. Okay, now in the existing methods, it has been observed that complete charging discharging data are essential, okay, for them. But here, in our case, partial charging data we can use. Between 10 to 20 minutes of data is sufficient. Like approximately, we have used 15 minutes of data. Okay, so that's why I've just written this range 10 to 20. You can actually use between 10 to 20. So, and special kinds of probing signals are necessary here. Okay, but here we only can depend on the existing partial charge data. So we don't need, like always, we may actually not need probe signals. Now cycle numbers are also necessary here, but here it is like some differential voltage based feature vector we have proposed. So that feature vector we will, like I will explain you how actually the feature vector has been formed. So here the battery models, for these battery models we need lot many number of model parameters which may be unknown to you. Okay, and here we need, because we have the partial charging data of 15 minutes, so that we just need one time training. Okay, that's it. And here this can be, most of the methods they are actually can be used for offline estimation. Okay, but this can be used for online estimation. Now, as I said, so this, all these things I have already spoke in the previous slide. So here in our case, so the training and testing batteries that we have used, so altogether we have used around 18 batteries for training testing purpose. Okay, so I'll be just showing you some results afterwards. So here in our experiment we have used two different types of batteries. One is type 1, one is type 2. So type 1 batteries that we have considered here, it is of 3 ampere hour. So this is typically, this is called 3000 mAh. Okay, so what actually you might be knowing. So this batteries has been used for training purpose, and for testing purpose we have used it type 2 batteries. So that is 3500 mAh. Okay, or it is 3.5 Ah, but they are of similar electrochemistry. Okay, so here we have used lithium cobalt oxide chemistry. That same chemistry it follows. Okay, see, it is like whatever we have proposed that can be also applicable to other kinds of electrochemistry, but for that we need some training. So for training that, in order to train our proposed method, so we need some time to train our model with corresponding to that kind of a data. Okay, that's it. But this method is also applicable in such scenarios where the electrochemistry is different. Okay, but here we have just tried to show you the results, same electrochemistry but two different capacity battery. Okay, one is for, one has been used for training purpose, another has been used for testing purpose or validation purpose. So here, how actually the design, like how we have actually designed the feature vector, that I have like here I will show you. Suppose this is actually a battery model. So this is typically in the literature it is called a electrical equivalent model. Okay, so you can see electrical equivalent means it has those parameters, like this is a voltage source symbol. Okay, and this is a resistance. These are two resistances that I have shown here. This is the voltage, like terminal voltage. Suppose if you take a battery, if you tap the two terminals, plus minus terminals, so the voltage that you get, this is this voltage. Okay, V, and the current that is going like in this direction, it is basically the battery current. Okay, now typically in literature you will find that they have only one single resistance, this RF you can find. So RF I have denoted here, but generally it is called as RI. Okay, so that is internal resistance. Now here I have just considered another resistance which is called the RACI. This RACI, it corresponds to solid electrolyte interface layer resistance. Okay, because our battery degradation happens due to the growth of this resistance. That's why actually I have kept this RACI as a separate resistance. Okay, and accordingly actually, like I'll show you that how the feature vector has been considered. Now if you see this circuit, so this is the current, this is the voltage which is denoted at this end, like from across these terminals. Now from this point to this point, the potential that I've shown here, it is called the VACI. Okay, but this is actually the net battery voltage, terminal voltage. This voltage source that has been shown here, it is called the OCV, that means open circuit voltage. Open circuit voltage, why the name is like that? Because if actually this, it is not, the battery is not connected to a charger or to a load, so it is basically open circuit. So that means no current is, ideally no current is flowing through this circuit. So if no current is flowing through this circuit, so that the voltage drop across this resistance and this resistance, they are basically 0. Okay, so if so voltage, you know that voltage is given by IR, so I times current times the resistance. So here the drop will be 0, here the drop will be 0 if I becomes 0. Okay, now under that situation, whatever voltage that you will observe here, that will only be this voltage, which is the VOCV. That's why the name open circuit voltage. Okay, so now this is actually a typical equation which is commonly known in the literature as Coulomb counting equation. Okay, Coulomb counting equation is something where so Coulomb is basically the unit of charge. Now charge is basically given by the product of current and time. Okay, so here you can see it is basically this equation is in discrete time. Okay, so you can see it is actually in discrete time. Okay, so discrete time it will be because when actually we are acquiring some data, like when some data is acquired by a measuring instrument, so it is basically coming in samples, right? So it is not that like it will have some, so depending on the design of that equipment, like either the data can come in every 1 second or every 0.1 second or maybe every 5 seconds. Okay, it depends. Okay, now so it depends on the sampling rate at what actually you are collecting the data. Now this TS actually denotes the sampling time. Okay, and this IK, it is basically the current. Okay, and K denotes the time instant. Okay, kth time instant. Cmax is basically the maximum capacity of the battery, and here the battery state of charge, you can see here, this is basically corresponds to that value which is at k minus 1th instant, and this SOC value, it corresponds to the kth instant. Now if I have to get the value of state of charge at kth instant, so I need the information of battery state of charge at k minus 1th instant plus the increment that we get. Okay, and this increment, you can see I into T is basically the unit will be in coulombs. Okay, and this Cmax, it is also having the unit of coulombs. So that means it is a ratio. So this ratio is basically, it is dimensionless. Okay, so therefore state of charge is basically a dimensionless quantity. Okay, that you can see. So both sides, it is balanced. Now once actually you know the value of battery state of charge at k minus 1th instant, so next instant value you can actually compute by using this equation. Okay, only you need the information of current. That's it. Now next instant, if you want to make again SOC k plus 1, so that time you have to consider SOC k. Okay, so in this way, iterative way, it will go on. Okay, so you can actually write a for loop if you have the information of current and sampling time and max capacity. So you can actually write a for loop like in whatever platform you want, be it MATLAB, C, or maybe Python. Okay, so there actually you can compute the battery state of charge. And battery state of charge is not directly measurable quantity. I am telling you, directly measurable quantities in the context of battery is battery current, battery voltage, and battery temperature. Apart from this, nothing can be measured. Okay, and whatever actually we'll discuss here, apart from these three quantities, nothing is measurable. So either you can derive it from somewhere from the information of these three quantities, but it is actually, those will be derived quantities. So battery state of charge that I have shown here, it is basically a derived quantity, not a directly measurable quantity. No device is there which can give you a measurement of battery state of charge. Okay, so you need the information of current, you need the information of the sampling time, and you can actually compute it like this by following this equation. And because it is a summing, like it is basically, if you realize this in continuous time system, so this k is basically the time step in discrete time, right? So now if you consider this in continuous time, so it will be like a integration. Okay, so this is just like integrating something. So I am summing here, so you can actually basically integrate. Okay, now so therefore it is basically accumulating something, accumulating charge in this case. That's why the name is coming Coulomb counting. Okay, so coulombs are getting counted here. That's why the battery state of charge, it is actually computed in this form, in this way. Okay, now you see that VACI, this is basically the voltage across these two terminals, like from this point to this point. Okay, this is, you can think that this is like a ground. So from this point onwards, the potential is VACI. This is basically simply Vk minus Rf times Ik based on this up to here. So this is called the Kirchhoff's voltage law. Okay, so from here you can find out. So potential at this point, it is basically the potential at this point minus the potential drop here. Okay, so this is basically balanced on both sides. Okay, so Vk is basically the sum of VACI plus I times Rf. Okay, so therefore actually VACI we can write like this, Vk minus Rf times Ik. Okay, now Rf, actually what is Rf here? Rf is the fixed internal resistance of the battery which doesn't change with aging. Okay, so that's why we have separated out Rf. Okay, we have not considered one single parameter Ri. So we want to show you that there is a fixed part and there is a variable part. Okay, so internal resistance, whatever initially the battery had, so we are considering it to be fixed. That's why Rf has been denoted as the fixed resistance of that battery, and RACI is basically it will actually consider all that change in the resistance that is happening due to the formation of ACI layer, which is basically more than 90% of the like ACI formation is basically it contributes more than 90% of the battery degradation. Okay, there may be some other mechanisms, but they are negligibly, they are very small. Okay, but I'm not discussing here right now. So there are certain other mechanisms, but 90% of the degradation happens due to ACI. Okay. Okay, so here delta RACI is basically, it is the increase in the internal resistance due to change. Like delta means there is a change, right? So delta RACI is basically the increase in the internal resistance due to the increase in the thickness of the solid electrolyte interface layer. Okay, as ACI layer which is formed on the anode surface, the thickness is gradually increasing. So due to the increase in the thickness, the resistance will also increase. So now the increase in the internal resistance will be reflected here. Okay, and here RF, how to compute RF, that actually I have shown you by in terms of a waveform here. So this is something like the battery was subjected to discharge. Okay, initially. Now once actually the battery was subjected to discharge, so all of a sudden what happened, that after some time you are basically stopping the discharge mechanism. Okay, so therefore it has been denoted here as end of discharge point. Okay, so this point. So suppose you discharge the, like suppose you connect the mobile phone and like suppose if you open some app. Okay, now if you open the app, so battery is getting drained gradually. Now if you close the app, if you just keep the phone idle, that means you are basically stopping the discharge mechanism, right? So that time it is basically, it has reached that stage of end of discharge point. Okay, now what will happen? So because it is a electrochemical device, so there will be like a relaxation time, like you are basically not drawing any current. Like whenever you are running some app, some current will be drawn from the battery of the phone, right? Now if you are not using any app, so that means it is idle condition. That time due to chemical equilibrium, so due to that equilibrium stage, the current will reach, like once it has stopped, the current is automatically, it will be zero. Okay, so no current is getting discharged, you have stopped already. So that time the voltage, like initially the voltage was falling like this. Now once you have stopped, so there will be a sudden jump from this point to this point. This point is like due to the relaxation time. Okay, so here how to compute RF, that actually I have shown here. So due to a incremental, like due to a change in the current, so there is an incremental change in the voltage levels. Okay, so VEOD, it denotes the voltage at end of discharge, like this point. This point maybe it is how much it is, maybe around 2.6 something. Okay, and VSOR is something at this point. Okay, so this current is this current, no, this is actually this current, if I see, it is 3 ampere. Okay, now this current is 0. So basically the difference is 3 amperes. Okay, so therefore you can see here that VEOD, there is a change with the VSOR. SOR is basically the start of rest. Now once the discharging has stopped, so the battery has undergone in the resting phase. Okay, so at that point, so there is a change in the voltage. So at this point, whatever may be the voltage at this point of the current, so there is this is the voltage. Okay, so therefore those points if I take and if I compute the difference, that will give us the change in the voltage level due to the change in this current, that will give the resistance. Okay, so we are following the same Ohm's law that you are knowing. Okay, V equal to IR. Okay, so now once, so this is how RF can be computed. Another thing that I'll show you here, that initially I've shown you one probe current, right? Probe current is a current which is having very small magnitude. That is maybe 0.2 C times the rated current of the battery. So now if you actually accumulate that battery current, and this K belongs, like it is actually for denotes the discharging phase. Okay, that's why I have written here. And IB actually in this case it will be negative. Okay, so in order to count up that negative, because current cannot be negative, right? So but in while actually we show the discharging phase, we have to show it in the negative direction. That's it. Because while the battery is getting charged, the direction of current flow, and while the battery is getting discharged, the direction of current flow, they will be opposite. Okay, so if the IB is, in our case it is negative, that's why a extra minus sign has been put here in order to count up that. Okay, mathematically. Okay, so basically this is summation of that probe current, like whatever is there in the discharging phase, and multiplied with this time, sampling time, so that will give us the capacity. So this capacity typically it is known as the target. So this capacity we will use it to compute the target state of health. Okay, so that's target state of health actually I'll show you later on. Now here I'll just show you some voltage versus battery state of charge plots. And suppose if you see this first plot, this is terminal voltage versus state of charge. Okay, and different colors has been used. You can see this is cycle number 1. Okay, when the battery is new condition, so that time the state of health will be the highest. Okay, now this is actually the cycle number 250, means after you have already discharged the battery for 250 times. Okay, so that time the state of health will reduce. And when the cycle number is 500, that means 500 times you have charged or discharged the battery, so the state of health will even reduce further compared to the previous case. So gradually when it reaches cycle number 1000, so at this point the battery state of health is the lowest, right? So what happens, that as the cycle number increases, the battery state of health basically it decreases. Cycle number increases from 1 to 1000, state of health will decrease from the max to the like whatever value it may be. Okay, so now under that situation you can see there is a interesting fact that terminal voltage has been observed across this battery state of charge. So it has been plotted, and you can see that at cycle number 1, this is the plot. When actually the cycle number has increased, so this has shrinked and it has actually gone to the left side. Okay, so in lesser time actually it is reaching this level. You can see the time, like not actually lesser time I would say, but it is shrinking. Okay, so it has actually reached this level at a lesser state of charge level. Okay, so now as the battery is aging, so you can see this is the direction of movement of this battery terminal voltage. So here the green color, you can see that here the battery voltage has reached the maximum value when the battery state of charge is almost close to maybe 68% or so. Okay, compared to the first case when it has already reached around 90%. Okay, so this is actually the phenomena which has been observed as the battery is aging. So this is basically the direction of aging. Okay, from this right side to the left side. And the same thing, like this is basically the terminal voltage, that is the V from the circuit model that we have shown. And this is basically the curve which corresponds to the VACI voltage versus the battery state of charge. Similar kind of characteristics we have observed here. Okay, there is also a shift or a shrinkage, like due to the degradation of the battery state of health, as it reduces, this curve will shift to the left side. Okay, just like this. So VACI is basically, it is reaching at this level when the state of charge was even less compared to the first cycle, right? So this is basically an indication of aging. Now, actually, I will just show you that how the VACI voltages has been computed, because VACI voltage, it cannot be actually directly measured. Okay, so this is actually just mathematically we have established it. Okay, so VACI is VACI voltages between two successive points. So that graph actually is there. I will show you. I'm just showing you mathematically how it is computing. Then actually I will show you the graph from where there also you can see. So two successive points. Suppose you choose K and K minus 1. The voltages corresponding to K and K minus 1, the difference will give you the delta VACI K, right? And that you will notice in the y-axis of the graph. Okay, so that I'm telling you beforehand. And target SOH computation is based on the probe cycle. So probe cycle current was IB. So based on IB, we have actually shown you that capacity can be found like this. This capacity we will use it here. Okay, so battery state of health is actually computed like this. Okay, it is with respect to the C max, that is the max capacity. And Coulomb count computation actually between two successive points, it is basically this delta QC. It is basically the summation of I times T. This is actually in units of coulombs. Okay, and this has been actually considered in such a way that whatever may be the Cmax, like whatever may be the Cmax max capacity, so at every 1.5% like change in the delta, like in 1.5% of Cmax, we are actually like computing like whatever delta QC is there. Corresponding to that, there will be like a delta VACI. Okay, so that I'll show you in one of the graph. Okay, so that is actually to actually assume that how much actually capacity has lost. Okay, now when actually I have shown you the first slide, that design of feature vector. So this is basically the feature vector that we are trying to establish. Now here, based on initial 400 cycles of data, okay, so we actually have tried to like based on that information, we have tried to like form some features. Okay, so features actually are in terms of the ACI voltages. These are basically the derived voltages based on those partially charged discharge data that we have. Okay, so this is actually based on one point. This is another point. So similarly up to 9 here. Okay, so if we have to compute delta VACI up to 9, we need actually VACI number of VACI voltages. We need 10 points, right? So then only we can get the differences like this up to 9. And we need the temperature, that is the average temperature of the battery. Okay, so that this 10 features we need. So these 10 features will be going to a neural network model, and that will actually help us to compute the battery state of health. Okay, so that I'll show you. Now here, this graph actually I have just the mathematics I have shown you here. The VACI voltage, how it changes with battery state of charge, that actually I have shown you here. How to actually select? Like initial value of the VACI is selected based on the battery state of charge level. Like if it is between say 80% to 60% battery charge, so we can actually take it around 3.7 or something. Okay. Now, what is delta VACI that we have defined? So suppose this line corresponds to VACI 1. Okay, these are actually, this is voltage versus SOC. So every point you take, so that is corresponds to a VACI. So now this point is VACI, this point is VACI 2. Accordingly, this is VACI K, this is VACI 10. Okay, so we have considered 10 points. That's why up to 10. Now K is some number between 1 to 9. Okay, something. So here you see that if I just show the difference between VACI 1 and VACI K, that difference is basically given by this. Like, okay, so in similar to like similarly different other points are computed. Okay, now here VACI K has been plotted with respect to battery state of health. So here we have just shown you that, and this is actually there is a shrinkage in the there is a shrinkage in the y-axis that is denoted by delta VACI, and there is a shrinkage in the y-axis that is actually called the capacity loss. Okay, that's why it is delta QC. Okay, so delta VACI versus SOH, how it will vary for different like cases that we have shown here. Delta VACI, it is at the lowest phase, and here due to aging actually it is happening like the magnitude is increasing. Okay, so this is happening due to aging. Okay, all this information we will use here for the to train the neural network model. Now this is actually the charging and discharging protocol that we have used here. So constant current charging at 0.8 C, sometimes 1 C, 1.2 C, okay, like that, depending on the rated current of the battery. This is the constant voltage mode charging. It will be at like max voltage is 4.4 volts for this kind of battery that we have used. So that's why it is at 4.4 volts, and constant discharge at 1 C and 1.2 C. Okay, so this is for the discharging phase, and every 50 or 125 cycles, so we are putting in between every 50 to 125 cycles of normal charging discharging, we are actually proving a probe, like we are putting a probe cycle with CCCV charge and CC discharge at 0.2 C rate. Okay, this CC actually takes this 0.2 C rate, and CV is actually depends on the voltage level. Okay, this voltage, and CC discharge is this. So I have shown you the graph already, the standard charging profile, so that it will follow like that. And this is basically the state of health estimation part, where we have a target SOH that, like, if we try to estimate the battery state of health, now estimation has to be compared to some reference, right? So how actually the reference will come? That reference has been created. So it has been denoted by the target SOH. This target SOH is already computed based on this, the probe cycle. Okay. Now here battery state of health estimated value will come from a neural network. Okay. So now we will compare the results which is obtained through this probe cycle, that is target SOH, and the another one, that is the estimated SOH, which is computed from the neural network model. Okay. Now here actually the schematic diagram of the artificial neural network has been shown to you. So here the training of the artificial neural network is done by the feature vectors that we have designed, and the target value, that is the SOH. So here you can see there are actually input layers. Okay. So input nodes, actually you can see that all these features like in the feature vector, whatever components we have, it is given to this input layer. Okay, and there is one hidden layer, okay, which is having 100 nodes. In our case we have considered this, and there is a single output node that you can see here, and from here you are getting the state of health value. So state of health is basically this. State of health is giving you the estimated one. Okay, so which we have shown here, and this is basically a metric which will tell you that how much is the error between the target value and the estimated value. Okay, and we are taking the absolute of that, because sometimes actually the estimated value can be higher than the target value. Sometimes target value can be higher. Okay, there can be some sign changes. Okay, plus minus. That's why in order to take care of that, we have considered the absolute modulus of that. Okay, and this is actually the training and testing phase, in which we have split, like as I said, that we have used around 18 cells testing and training purpose. So here different, actually at different scenarios, charge times, we have charged the batteries. So we have written here, and we had a thermal chamber where we can cycle the battery at different temperatures. Okay, so here the testings, that the battery tests were done at two different temperatures. One is at 45 degree, one is at 25 degree. So I will just show you the results corresponding to both the temperatures. Okay. Now these are some, so these are actually some of the symbols which are associated. Now see, we have only 400 initial cycles of data. Okay, partial charge discharge. So now that will roughly be, you can see that if the state of health from 100 to 96%. Okay, 400 cycles of data. Now if we have to depend on a very small amount of data, so we actually need some extrapolation. Okay, to extrapolate the to extrapolate that characteristics, so we need a battery electrochemical model behavior, so that actually we can actually tell you that with some partial information this can be the trend. Okay, so in order to do that, there has been one battery model has been considered here. Okay, so which is having some electrochemical parameters. So I'll just briefly tell you. Okay, not going into much details. So these are actually some of the parameters like symbols that has been used here. This corresponds to the specific internal interfacial area of the anodes, initial side reaction current. This is actually the area of the anode. Okay, this is the thickness of the anode. This is the cycle time, charge transfer coefficient of anode cathode, or some other universal constant like Faraday constant. Okay, and also there are certain other, like this is charge transfer resistance, which depends on the universal gas constant, temperature, and all this interdependency is there. Okay, you can see here. And as actually the battery that ACI layer thickness is growing, so in order to quantify that, we have used a this quantity. This is called delta ACI. Delta ACI actually denotes the ACI layer thickness. Okay, because as the thickness increases, then only the resistance will increase. Okay, so there are other set of parameters which are involved in the battery. Those are actually the open circuit potential. Okay, this is actually this is mostly in the electrochemical properties. Okay, so this is the solid particle lithium concentration. Here you have the over potential terms, initial ACI film resistance, molar mass, the ACI layer density, all these things. Okay, so you actually you may not be getting all such things, because these are totally related to some electrochemical fundamentals of a battery. So but I'm just telling you because we have actually gone through this approach. Okay, now once actually you I've shown you the symbols of those parameters. Now we are basically trying to extrapolate the voltage curves based on the initial 400 cycles of data that we have. Okay, so basically we are trying to extrapolate the charging voltage curves for the complete lifespan of the battery. Okay, only based on the initial 400 cycles. Okay, just like I have shown you before. So the governing equations actually, they are actually like this. Okay, so this is the expression of capacity loss, which depends on all these parameters that you can see here. This is the RACI, like how the RACI changes. This is the RACI in the initial phase, that's why it is written as RACI 0, plus the delta ACI. As the thickness increases, the RACI will automatically increase. And this is the ACI ionic conductivity. So I've shown you here also, it is there. Okay, so now this is actually the expression of ACI layer growth, how it looks like. So this is in terms of the Q loss, like Q loss is having this whole term. Okay, and here we are just we have tried to just relate delta ACI in terms of the Q loss, and actually this relation, this is basically the relation of the increase in the or the change in the ACI layer thickness, okay, with the capacity loss. Okay, this is basically the electrochemical reaction equation. Like, so this is basically the relationship, okay, between delta ACI change with Q loss. And here if you just substitute, so RACI actually will be like this. So this is delta ACI that we can show. So delta ACI, if it is this whole term, this you can just replace here, and you will get from this equation, we will be getting this equation. Okay, so now ACI layer thickness versus cycle number, that governing equation I have just shown here. That if you actually think that from cycle number J1 to J2, where J1 actually is at a later stage, okay, that's why J2 is greater than J1, we have denoted here. The change in the ACI layer resistance, how actually it looks like. It actually looks like this. The delta RACI J2 comma J1, it is basically some PC times delta Q loss. So change in the RACI, it depends on the change in the Q loss. Okay, PC is this whole term. Okay, so PC is actually given by this term. Okay, so we have actually found from here only. Okay, from these equations only it has been derived. So PACI, this is the whole form. So now why actually it has been considered as a single element. Okay, single parameter. That actually I'll tell you, because the when actually the battery, like if you test a battery, only voltage, current, temperature information is available. Now if you have to know all these parameters, like what is the thickness of the, like what is the length of the electrode, what is the cross section area, what is the ionic density, all these things, so you need actually lot of investment in, like you have to do scanning electron microscopy, you have to do some XRD analysis, all such things. Okay, half cell analysis, all these techniques are there, but they are very much sophisticated, and then sometimes you may not also get some like all information. Okay, and it is not available also in the literature, you will not get, very limited information is available. Okay, so therefore getting all these parameters, so it is not always feasible, because if you don't have the correct set of parameters, you actually cannot do some computations which are in real time, right? So therefore, in order to make things simple, what actually we have done is that this whole thing we have considered, we have lumped together with one single parameter that is denoted as PC, right? So now it is coming in the simplified form that you can see here, where the delta RACI that you can see here, it is basically the difference between the RACI at those respective cycles. Okay, RACI corresponding to J2 cycle, J2th cycle, minus the RACI corresponding to J1th cycle. That difference will give you the change in the change in the RACI value, like when actually the cycle number is changing from J1 to J2. Okay, so similarly Q loss also we can compute like this. Okay, so this is the definition of delta Q loss and delta RCA. Okay, now this PC actually, whatever actually we have denoted here, that is actually a lumped parameter we have considered. So we are assuming that all those effects will be actually inside that PC, right? Now PC alone has to be estimated. How actually we will estimate PC? So in order to estimate PC, so we have used the very popular method, which is called the method of least squares. Okay, so this is very much popular method when actually we go for curve fitting. Okay, so if you see that PC has been actually written in such a way, so this is this bold symbols, you can see this denotes a vector, right? So this is basically a vector. It is written in a row vector kind of a form with transpose. Okay, so here delta Q loss have all these components, and delta RACI have all these components. Okay, so here this 50, 100, 400, all these actually are different at different stages of the battery aging, right? Now you see that delta RACI was equal to PC times delta Q loss. So therefore, based on that, you can actually form this kind of relation, where delta Q transpose delta Q whole inverse delta Q, ultimately it will, like this equation will come. Okay, so whatever actually I am showing here. Okay, so it has been framed in such a way that we can actually use the least squares approach, and we can find out the estimate of PC, which is the unknown parameter, right? Now in order to do so, we need the information of delta Q loss and delta RACI. So how actually we will find out delta Q loss and delta RACI? This is actually the way that I have shown here. So delta RACI, suppose this is 50, it is basically RI 50 minus RI 0. So the internal resistance at say 50th cycle minus say internal resistance at 0th cycle. Okay. Now internal resistance at 50th cycle is basically the fixed resistance plus the delta RACI at. So in this way it is computed. RF is basically some RACI, which is like in the initial 0th cycle, it is basically 0. Okay, so in this way it is computed. Okay, now here and Q loss is basically the change in the capacity. Okay, that is actually you can find out. Now this is actually some this is the internal resistance versus SOH curve, and it is a measured and fitted one over the initial 400 cycles. So one is basically the measured one, blue one, and the fitted one is shown here in the red dots that you can see here, and we have observed that the correlation coefficient is around 0.96. Now this is actually the this is a VACI versus SOC graph for different stages of aging. Like that's why it has been written here that when SOH was 99%, so that time this is the measured one, this is the, so you can see that this is actually the first one. Okay, so if you think that this is the SOH 99%, so this is actually the first graph, like blue one and the dotted one. After that, the yellow one, which is corresponding to SOH 96, this is the second one. Okay, so due to, like, as the battery health is gradually decreasing, in this way it is decreasing, right? So as it is gradually decreasing, so you can see there is a shift. There is a shift that we have observed before also, like ACI layer voltage, it actually shifts to the left side due to the effect of aging. Like VACI has reached this voltage when the SOC was much less compared to the VACI when it was around 99%. Here the battery SOH is 91%. Okay, and in these four cases, so the correlation coefficients has been computed and it has been observed that they are very close to 1. You can see here. Okay. Now, these are the steps which are involved here in the extrapolation process of the voltage curves. That is the VACI. Okay, so we have initial 400 cycles of data, but we are trying to extrapolate in terms of that electrochemical model equations that we have, that I've shown. Okay. So now you can see that this VOCV, it is basically the VACI minus delta RACI based on the circuit that we have written. Okay, VACI K is basically VK minus RFK, that is basically the circuit based on that. Now based on the VOCV computations, so here in the first step we have computed VOCV based on this equation. Okay, so VACI we have information, delta RACI also we have information, so we will get VOCV. Okay, now if we get VOCV, we have the SOC information, so we can basically fit a polynomial like this, which is of nth order. Okay, so nth order, actually I have just shown you, it is actually like a generic sense. Okay, now this n can be anything, like it can be 3, it can be 4. If it is 3, it will be a third order polynomial. If it is 4, it is a fourth order polynomial. If it is 5, it is fifth order, like that. So generic way of like how to represent this polynomial fit, it is actually like this. That's why I have shown you. Now once actually I have computed the VOCV, this is actually based on, like, this is based on the relation of the SOC with OCV. Okay, so this is coming from a lookup table kind of a relation. Okay, because it is a polynomial fit. Now you can see that at step number 3, so this is this actually here it is like this equation in step number 2, it has been slightly modified and it has been just framed in such a way that if I actually think that this equation is at 100% SOH, now what will happen if the SOH percentage reduces? That time what will be the VOCV relation? So because ultimately when VOCV is basically related to battery state of charge, so when the battery state of health was 100%, whatever relation it holds, the lookup table, when the battery state of health has reduced maybe by 5%, so that time the relation between battery open circuit voltage and the battery state of charge will no longer be the same. Okay, so if it is not same, then how the change will happen? That change actually will happen according to the step number 3. So here you can see VOCV, this is at X% SOH. So at X% SOH, the same equation has been just modified. Okay, so this, if you consider X to be 100, then it will again come to the step number 2. Okay, so it is actually very generic way it has been written. Okay, so now once the OCV relation between this X% SOH, it has been established, so how we can actually go to the step number 4? Here we will get the VACI information, which is VACI is basically VOCV based on this equation. You can see VOCV plus delta RACI times IK. Okay, this one. So all this VACI, VOCV, delta RACI, they all depend on the state of health. Okay, they are all dependent on state of health. So therefore, except the current doesn't depend. Okay, now another actually beauty of this, like considering this kind of equation, is that this is actually independent. This is independent of the value of like the charging rate. Like I have already deducted the RF times I from this and I have computed VACI. So from VACA only we are getting all such like information which are required for the training of the neural network. Okay, so it is actually independent of the charging rate. Okay, because already in the equation we have deducted the IK part from here VK. Okay, now here as per this equation, so delta RACI is basically, as per our previous equation, delta RACI is equal to PC times like delta Q loss. So based on our this equation, you can see based on this equation. Okay, so here it is just estimate, that's why it is written as a hat symbol. Okay, that's why it has been written like this, because it is an estimated quantity based on the least squares we have estimated it. So it follows the same equation and it corresponds to the X% SOH. Now similarly delta Q loss at X% SOH you can actually compute like this. So when SOH was say 100%, so that time delta Q loss it is actually basically it will turn out to be 0. Okay, so means when it is at the maximum capacity, so that time there is no Q loss, that's why it is 0. Okay, when actually this X is SOH is ideally 0, that means the battery is dead. That time when what it will be, you can see that delta Q loss will be totally equal to C max, that is all capacity has been lost. Okay, so it follows the mathematics like this. Now this is actually the flow diagram. I'll just quickly go through. Like this flow diagram of the proposed approach, it shows like it is basically designed in such a way that it covers the complete lifespan of the battery. Like when actually you have all the battery data available to you. Okay, one such case we have considered. Another case we have also considered where all the battery data is not available. Okay, in this case when complete lifespan of the battery data is available to you. Okay, so that time what will be your approach? It is like you need a one-time offline training where current voltage and temperature data from the full life cycle of the battery will come. So that will based on that you have to generate the feature vector and the target vectors. Okay, and you have to train the ANN model. And here this is cycle wise. So cycle wise online SOH. Now here based on a partial charge discharge, you actually get a current voltage temperature data. Based on that you will have a feature. That information and this information you both need in order to estimate the SOH based on the trained artificial neural network. Okay, artificial neural network has been already trained with the in this offline learning process. Okay, now once it is cycle wise, it is in online phase real time. So as you are getting the current voltage information, so automatically you will get the feature vectors. So that feature vectors it will come and it will actually help you to generate the battery SOH estimate based on the trained ANN model. Okay, now a slight change will happen if we don't have all the battery data available. Okay, so here what is happening, we have only 400 cycles of data, that is a partial data. So here we are doing a extrapolation of the battery voltage for complete lifespan of the battery. That extrapolation is happening based on that electrochemical battery equations that I have shown you. Okay, based on that. So based on that, afterwards the feature vector has been generated. Okay, along with the target vector, that is the SOH. Training has been done and same thing is happening here. Okay, only change is happening here. This extrapolation part is the extra part. Okay, which was not there when the battery data was available to us. That time we don't need extrapolation, right? Extrapolation is only needed when we don't have the rest of the data for the lifespan of the battery. Okay, so this is actually the this is actually the proposed method when we don't have the battery data available to us. So the ANN will also give the SOH estimate based on the trained ANN model and the generated feature vector from the current cycle data what actually it is feeding. Okay, so here as I shown that before that at different temperatures we have tested two different temperatures, one is 45 degree, one is 25 degree. So this is actually the state of health versus the cycle number plot. So here we have shown that target SOH, this is computed based on the probe cycle test, that is considered as the reference, and estimated SOH is computed based on the artificial neural network, and you can see that it is matching quite good. Okay, and when actually the temperature has been changed to 25 degree, that time actually this is basically the outcome. Okay, you can see that. So this is something where the state of health, like target and estimate, both has been compared. And here this corresponds to type 1 batteries. So in one case, the charging current was used as 0.8 C, and the chamber temperature was considered as, this is a thermal chamber which is enclosed. If you actually program it that you have to maintain it 45 degree, it will maintain 45 degree throughout. And once you change the level 25 degree, it will maintain it throughout. No fluctuation will happen. Okay. So now under those two scenarios, it has been observed that target SOH and estimated SOH, they are pretty close. Okay, you can see here in this case and in this case also. Okay, so this is based on the type 1 batteries that has been based on which the artificial neural network has been trained. Now here you can see that charging rate has been changed. Now in the previous case, what happened, that charging rate was kept constant and chamber temperature was changed. Now in the second case, chamber temperature was kept constant and the charging rate was changed. Okay, here it is 1.2 C, here it is 1 C. That time also our proposed method, it is like performing quite good. Okay, you can see here. Okay. Now this is another case where we have tried to validate our approach based on a type 2 battery which is of 3.5 ampere hour capacity. That is totally like, it is only used for testing purpose. Training has not been used based on these cells. Okay, so here you can see that here also it is like pretty close. Okay, so once it is trained, so that trained model, it is able to like give you the battery state of health estimate quite close to the target SOH. So this corresponds to charging rate of 0.8 C at chamber temperature 45 degree, and this is at chamber temperature 25 degree, keeping the charging rate constant at like fixed at 0.8 C. Okay, so you can see they are very much close. You can see the estimated and the target values. So here I've just shown you like this is basically a error plot, like bar plot of different error matrix. This is mean absolute error, this is standard deviation, this is maximum absolute error. Okay, so for 16 batteries I have shown you here. So here this is different colors has been used to denote MAE percentage, SD percent, and so mean absolute error has been like here mostly it has been shown that below 1% we have achieved so far, and also standard deviation of 0.7 we have actually achieved. Okay, except one or two cases. So in this case only, this is a just like an outlier. Okay, so you can see that here only in, it is slightly higher like compared to the other scenarios, one or two cases you can see. But apart from that, we are getting satisfactorily, like they are actually reasonable performance we are getting out of our proposed approach. And these are some of the summary points that I have written here. You can see that based on our proposed approach, so you can actually think that this is an online solution to develop so a practical problem of how to actually estimate the battery state of health, even if you have a partial charging data, and also with approximately only 15 minutes. So I have just written there 10 to 20 minutes. So you can actually use, if not 15 minutes, you can use 16 minutes also. Okay. So in our case, we have used 15 minutes of data, normal usage charging data. So that was sufficient to estimate the battery state of health. And also the proposed solution, it collects the current voltage, temperature information. It can actually collect from the existing battery management system, and it can be integrated easily to the BMS code. Okay. Now, and the training of the algorithm can be like we have used 400 cycles of, so even actually it can be reduced further if we actually again try. And here if we actually try for a new battery chemistry, if we want to apply our proposed algorithm, so what we have to do is that we need some approximately 45 days time in order to generate some training data for that, so that our method can be trained with that. Okay, so because for the same electrochemistry, if it is already trained, for you give any kind of battery, like any kind of capacity, it will give you the estimate. But if you change the chemistry, that time you need a retraining. Okay, so that is actually, that has to be done. Okay, because no method can be like universal for like all kinds of chemistries. It is not, it is actually not feasible. Okay, so so that is actually a much challenging task. Okay, so only that part needs some time. Okay, so if you just train it, then you can use it. Now another thing that we have actually observed, that the mean absolute error criteria was less than 1%, and our method actually is much robust, and that under different test conditions that I have shown you, at different, ranging from different temperatures, as well as charging rates, as we change. Okay, so even actually we have tested with different battery like capacities. Okay, maybe of electrochemistry is same, but the capacity is different. Okay, so for that case also we have shown that our proposed method, it is giving reasonable performance. And this is actually like a, like another practical advantage, I would say, that we need only one first cycle internal resistance data. So that resistance actually will, like when we have seen that VACI, when we have picked, okay, so one single point we have picked, and after that every 1.5% change in the with respect to the max capacity, like the Q loss, after that we have chosen again a delta VACI. In that way actually we are choosing. Okay, so initial point only one we need. And our proposed method, it is applicable for wide range of applications, starting from smartphones or electronic gadgets or electric vehicle applications, and various other sorts of applications, like ranging from biomedical to aerospace also. Okay, so I hope so I have actually came to the end of my slide. So these are some of the key references that we have followed, and and also one of our papers I have cited here. So thank you very much.
So, the dear participants, any queries? Is there any queries from your end?
If you have any question, please feel free to ask.
Okay, so I hope there is no query. Okay, so
And I hope from Ashish Kumar
Yeah,
Singh.
yeah. Good afternoon, good evening, sir. Sir, I have a question. Sir, when we are talking about fast charging of electric vehicles, so there is a technique known as differential partial processing of electric vehicle. So there we check the status of battery, and as per the percentage of charge the battery bank has, the different batteries have, we charge the vehicle. So we are not using the entire voltage or the entire quantity of the voltage, and instead of that we are using a partial portion of the power to charge the batteries. So, sir, can we relate this concept with state of charge of the batteries here?
Like, you are actually talking about any established technique used for battery charging in the EVs? Like, what
Yes,
do you say?
yes, sir. That is known as partial charging of batteries. So it is basically suppose we have a bank of batteries. So we'll first distinguish the amount of charge a battery has. For
Hmm.
example, one is having 60% or something. Some
Hmm.
battery has 40%. So it will check that particular status, and then it will charge accordingly, instead of charging the batteries together. So it optimizes the system, and the cost part and the efficiency part increases, and cost also is reduced. So how
Like,
can I correlate this concept with what we discussed today in your session about state of charge
okay,
of the battery?
you are actually talking about that how to actually apply this concept for a battery pack charging.
Yes, yes, sir. Yes,
Like
sir.
battery pack will have a collection of all different cells. Okay, so and each of those cells can be actually have unequal charge. So there we need another concept. There is a, it is called balancing. Okay, so you actually have a need to have a balancing. Either you can have a passive balancing approach, which is a low cost like approach, but it is actually there will be a loss in the energy, okay, in terms of dissipation. Or you can actually do a charge transfer based on this active method, okay, so which is called active balancing method, where whatever actually, like you are saying that a battery is having 60% charge, another having 40%, so charge from the 60%, like it is at a higher charge, so that will be first equalized, okay, charge equalization will happen, then actually the battery will get charged. So their balancing approach should also come into picture. Okay, and yes, actually this method is also applicable there. So we, apart from that, we also have to consider the balancing phenomena, because here whatever I have shown you, it is with respect to one single cell, okay, one single battery inside a battery pack. But each of those batteries inside a battery pack, they also can be actually like treated in the similar way, but depending on their respective charge levels, you first you have to do some balancing work. Okay, so what actually is also very important aspect in the context of battery pack. Okay, there you can otherwise that you can actually apply the approach that I have discussed today.
Okay. Okay, sir. Thank you. Thank you, sir.
Is there any other queries? Okay, so I think there is no query, any other query from the participants. So thank you, Professor Arijit Guha, sir, so for your beautiful sessions on battery. So thank you, sir, for your valuable time for us. Okay, I hope participants also getting a lot of information related to the battery charging, their chemical compositions and different characteristics. So thank you, sir, for giving your valuable time to us.
Thank you, Professor Ghosh. So I hope actually, like, I actually tried to like go very slow, because I know that there are participants who are from non-electrical background. So I tried much that if I can make them familiar with some of the terminologies related to battery and their characteristics. Uh, but there are actually certain terms which are associated with battery, starting from the electrochemical part also. So on the first place, like it is difficult to understand. So who are actually not from this background, but I tried in my way that how to make things simpler, and how actually we can actually see the overview of the work actually that we are doing. Okay, so I hope people have got some information from here. Uh, okay, thank you, Professor Ghosh, and thank you all the participants for your kind attention.
Yes, sir. The session was very nice. I hope they are able to understand all those things. Thank you, sir. Okay, so okay, sir. So thank you for your beautiful session.
Okay, okay.